Finite lists of sets are pleasant. Analysis, naturally, asks for families with arbitrary labels and operations extending forever. We will define indexed families, arbitrary unions and intersections, and then the lower and upper limits of a sequence of sets. Let I be an index set and X an ambient set. An indexed family of subsets of X is a function sending each index I to a subset A sub I. We write the family as A sub I indexed by I and I. The index set supplies labels. The ambient set supplies the universe. And each family member is a subset of that universe. A family is not merely the set of its distinct values. Labels and repetitions matter. A sub I may equal A sub j even when I and j differ. The union over I contains the points belonging to at least one A sub I. The intersection over I contains the points belonging to every A sub I. The quantifiers are the entire story. Union means there exists an index, while intersection means for every index. For example, if A sub t is the interval from -t to t for positive t, the union is all real numbers, while the intersection is only 0. The empty index set deserves its own convention. First, fix an ambient universe X. The union of an empty family is empty because no indexed set contributes a point. The intersection of an empty family is X. Every point of X satisfies the condition for every index in the empty set. Because there is no index that can fail it. The ambient universe is essential here. Without X, the phrase all elements does not specify a set. Set theory is fussy about this for excellent reasons. Now specialize to a sequence of subsets A sub n of X. Fix one point X and watch whether it belongs to A sub 1, A sub 2, A sub 3, and so on. There are two natural questions. Does X eventually remain inside? And does X return infinitely often? The lower and upper set limits answer exactly these two questions, point by point. The lower limit, or limit inferior, is the union over n of the intersection of all sets from n onward. For a fixed n, membership in the tail intersection means X belongs to every A sub n with n at least n. The outer union says that at least one such n must exist. Therefore X belongs to the limit inferior exactly when X is eventually always inside the sets. It may misbehave finitely many times. Analysis has agreed to overlook that. The upper limit, or limit superior, reverses the two operations. Intersect over n the union of all sets from n onward. For a fixed n, membership in the tail union means X appears in at least one A sub n with n at least n. The outer intersection demands this for every starting point n. Therefore X belongs to the limit superior exactly when X appears infinitely often. No matter how far we skip, X eventually appears again. For every sequence of sets, the limit inferior is contained in the limit superior. Take X in the limit inferior. Then some n0 exists after which X belongs to every A sub n. Given any n, choose n at least the maximum of n and n0. Then X belongs to A sub n. Thus every tail contains another occurrence of X. So X belongs to the limit superior. Eventually always certainly implies infinitely often. Consider the sequence that equals the singleton 0 for even n and the singleton 1 for odd n. The sets alternate forever. Apparently choosing one favorite singleton was too restrictive. Neither 0 nor 1 is eventually always present, so the limit inferior is empty. Both 0 and 1 occur infinitely often, so the limit superior is the set containing 0 and 1. Because the limit inferior and limit superior differ, this sequence has no set limit. We say A sub n converges to A when its limit inferior and limit superior are both equal to A. If X belongs to A, it must eventually stay inside A sub n. If X does not belong to A, it must eventually stay outside. Different points may stabilize at different times. Uniform punctuality was never part of the contract. Monotone sequences always have a set limit. If the sets increase, the limit is their union. A point enters at most once and then remains forever. For example, the intervals from -n to n increase to the real line. If the sets decrease, the limit is their intersection. A point leaves at most once and never returns. For example, the intervals from -1/n to 1/n decrease to the singleton zero. In either case, each point changes membership at most once. So limit inferior and limit superior agree automatically. An indexed family is a function from labels to subsets of a fixed universe. Arbitrary unions use an existential quantifier, and intersections use a universal one. The limit inferior contains points that are eventually always present. The limit superior contains points that are present infinitely often. And it always contains the limit inferior. A sequence of sets converges exactly when those two limits agree. Equivalently, every point eventually settles on a final membership status.